to the Tucson Amateur Astronomy Association June meeting. This is our member meeting that occurs the first Friday of every month, and we're delighted to have people with us tonight on Facebook, people with us on Zoom tonight, and also people actually in person tonight. So this is our first time of having in person and Zoom together, and we're hoping that everything works. There's been a lot of foundational work here to try to get things to go smoothly, so we'll hope that it does. So we will do our usual thing with people who are on Facebook and people who are on Zoom in terms of questions. If you will enter your questions into the chat, then we will address those at the end of the speaker's presentation. So people in the room, I will need to carry the microphone to you, and you'll need to ask your question over the microphone. So we'll have a little bit of a delay that we don't usually have in addressing answers to questions or determining what the question is, because we'll have to get the microphone to the person in the room here for that. But we expect that to all go smoothly, and we're just delighted to have all of you with us tonight. And we have Terry Lappin, who is helping us with the technology and with Facebook. And also we have Jim Knoll, who is helping us with technology and Facebook. So, so hopefully we will get all of your questions answered. Please, if you're on Zoom and you have your visual portion on, please make sure that if you are moving around in any way that might be distracting, that you turn off your visual portion for that. And also you can make sure later in the meeting when we have discussion to turn your audio on at that point. So tonight we have a really great speaker for us tonight with a really interesting topic. We have Dr. Kevin Wagner, and Dr. Wagner tonight is a postdoctoral fellow at the University of Arizona, and he has some really interesting research that he's done on imaging giant planets that are forming around young stars. So Kevin, if you're ready.
Thank you, May. Can everybody hear me? Should I raise this mic a little bit? How's that? All right, let me get the presentation going here. All right, how's this? Looks good to me. All right, so I want to talk to you about imaging giant planets around young stars. This is a relatively young field, probably just about a decade or so. So most of these images are going to be pretty new. And it's very related to the field of exoplanets. And also one of the goals that we're trying to do in a lot of these observations is to image the exoplanets themselves. So first I want to give you a bit of a background on exoplanet imaging. But first, a bit more on exoplanets in general. We now know of about 4,000 of them, or that's what I used to say. Now it's actually about 5,000. So I have to keep revising this in my head every time I give this talk. But planets that we've actually seen directly, and that means we've actually seen the light directly from the planet. We haven't detected it via some sort of indirect method, like the transit method, where the planet passes in front of the star and blocks off some of its light, which you can see in this diagram here. This is how we know of most planets, through these indirect methods. But planets that we've actually received photons from and been able to distinguish those as photons from a planet instead of photons from a star has only happened in about a couple of dozen cases. It's the number changes depending on who you talk to, but something like 10 to no more than about 100 directly imaged planets. And the reason why that number is a bit uncertain is because it's a bit hard to define what a planet is at the upper end of the mass range. We usually use the deuterium burning limit, but it can be kind of difficult to determine whether an object has burned deuterium or not. But this is what I tend to think of when I think of an image of an exoplanet, or what we would like to see in an image of an exoplanet. And of course, this is an image of our own planet, our own pale blue dot that Carl Sagan popularized. And instead of just seeing a fully resolved planetary surface, what we're going to see is just an unresolved speck of light. And everything that we're going to try to learn about that planet, we're going to have to learn just from resolving that one speck of light and possibly splitting it apart into a spectrum and things like that. But instead of this picture here where we have a dot that's clearly detected, or actually here there's a bit of a sunbeam in the way, which it's either pretty or a bit of noise depending on how you look at it. But in the case of exoplanets, we're going to be staring at these objects right next to very bright stars. So you can imagine if the sun were right next to, well, if you had a very bright star in this image, you wouldn't actually be able to see the Earth. The light from the sun here is, of course, the sun is quite far away from the actual image, and you still see its effects. So here's an actual image, or actually a movie, of some planets we've been able to image. This is the HR 8799 star. It has 4 super Jupiters. These are each about 4 to 5 times the mass of Jupiter. And they're on orbits of about tens of AU. The widest one here is at about 70 AU. And for reference, Saturn in our own solar system is at about 10 AU. So this thing is on the scale of multiple times our solar system. And these planets are very young. This system is less than 1% the age of our sun. And this is the only reason why we're able to see light from these planets at all. They're still young, they're still hot, they still have this heat. And well, this heat left over from their formation that ends up resulting in a higher luminosity, and then we're able to see the planets. If this system were as old as our own, even though these are giant planets, they're so far away from their star that we wouldn't be able to see any sort of reflected light. On the right, you're seeing an image of another system that's just a few times younger than the system on the left. This is the star SAO 206462. We tend to memorize quite a few of these telephone numbers studying young stars because there aren't too many of them. But what you see here is the disk of gas and dust around this young star. So there's a gap in the center. Part of that is because we've blocked out the light from the central star. Part of that is also because there is a gap of material there. And outside of that, you see this disk of gas and dust and this 2-armed spiral pattern that I'll say more about later. And again, this is on the scales of 40 AU or so, several times that of our own solar system. Or actually, rather this scale bar here is comparable to that of our own solar system. This would be at about the same location as the Kuiper belt in our system. Okay, so how do we make these images? One of the most important pieces of technology that we have for this is called adaptive optics. And what this allows us to do is to remove the blurring of the Earth's atmosphere. On the left, you see the contours of a star. If we were to stare at it and integrate for a little while, the star bounces around in the image, and well, it's not a very sharp image at all. But once we turn the adaptive optics system on, you can actually see that this is a binary system that's quite well resolved. This is actually the mirror that allows us to do this. So this is, in my mind, a pretty remarkable piece of technology. This is actually the adaptive secondary, or this is the secondary mirror of the telescope on the Magellan telescope in Chile. And it's actually adaptive, meaning that we can change its shape. And in this case, we're changing the shape about 1,000 times per second. And each of these little points that you see on the mirror is a magnetic actuator. And I think this is pretty cool because these not only hold the mirror in place, but they also allow us to change its shape. So this mirror, or the glass, is not actually connected to anything. It's just sitting on this bed of magnets, kind of hovering in shape and having its, well, hovering in space and having its shape changed 1,000 times per second. These are just kind of some fun images taken with the MEG-AO system. This was actually during an earthquake. So you can see the image on the top left is what it's supposed to look like when the system's working, nice and in stable conditions. And as the earthquake started, we saw the system try to keep up. It actually stayed locked on the target, but the image on the bottom right is what it looks like basically when the AO system isn't really working at all. All right, so another important piece of technology that enables us to image planets around other stars and also the disks and environments in which they form is called a coronagraph. So this was invented back in the 30s by Bernard Liot. And I don't think that he invented the name at the time. You can see the title of this paper was The Study of the Solar Corona Without an Eclipse. So this is his coronographic image of the sun. On the right, you see the solar corona just barely peeking out above the noise here. Of course, we have better, more modern versions. Here's an example of one that we typically use to image exoplanets. So instead of just a central occulting disk, this is like a pair of polarized sunglasses in which the polarization vector wraps completely around the image. So instead of just having parallel lines in order to block the polarization from one direction, we block the polarization in a different direction depending on where you are in the mask. And at the center, all of these tend to cancel. So this is a pretty small chip. It's etched on the order of the wavelength at which we're observing at. So here the different etches and this grading are about 10 microns apart. So that's a fast introduction to how we image planets. I want to get into some of the science and images that we've taken in the process. And the question that I want you to keep in mind, and one that I'll try to do some justice to throughout these next slides, is how do planets form and interact with their birth disks? And I'm only going to be able to partially do this justice because we only have a few case studies. This isn't a question that's been answered in any generality yet. So the first system that I want to talk to you about is PDS-70. So this disk is about 140 astronomical units across. So you could fit our whole solar system inside of here. It has a wide gap in the gas and dust. It was hypothesized when this was imaged back in 2012 to be due to forming planets within. So a pretty natural hypothesis is if you have a giant planet orbiting in a disk of gas and dust, that it forms a gap in the center or at its orbital location. And 6 years later, we imaged the system again with an upgraded AO system, and we were able to see the planet. So this is PDS-70b. In this case, with this upgraded system on a telescope, we were able to see the planet pretty clearly inside of the gap, pretty much right where models predicted it to be. This was a pretty interesting and exciting experience for me because I was actually over in Europe visiting the team that made this discovery a few weeks before they announced it. And that enabled us to use one of the systems that we have and built here in Arizona while this was still kind of in a secretive phase to get these observations in this pretty exciting mode. So the MEG-AO system that I showed you images of earlier was designed specifically to do adaptive optics at visible wavelengths. So not looking in the thermal infrared, actually, where most planets shine brightest, but when you have a very young planet that's still accreting gas, you can look for hydrogen emission lines. So the H-alpha emission line, we can actually see with our eyes in the red part of the spectrum. And this is where accreting planets emit a lot of their energy and a lot of their luminosity. So by performing adaptive optics in the visible and looking at this system that we happen to know there was a planet around, we were able to make this first observation of light generated in the accretion process from this forming planet. So everything that you see here in this image is taken in the narrow H-alpha filter. Over on the right, you see the same image overlaid on top of the infrared image, which shows the gas and dust in the disk and also some thermal emission from the planet. And by going through some mathematics from the luminosity that we measure in the H-alpha line, we're also able to measure an accretion rate or estimate an accretion rate. It actually ends up being an upper limit because we aren't sure how much light we're losing due to extinction from other dust in the system. But kind of remarkably, this planet is accreting at a rate of something like 10 to the minus solar masses per year. That's probably a pretty boring number for most of you. But what's remarkable about this is that that's the same accretion rate as the star. So in the process of forming, this planet is sweeping up as much material as the central star is, which, well, it came as a surprise to me. I expected the accretion rates when we were able to make these first measurements to come out as quite a bit smaller, but that's not what happened. There's been a second planet found in the system, so you can actually see it here in this infrared image, but it kind of gets lost and blended in with the signals from the disk. And this also kind of highlights one of our common challenges when we're making these observations and trying to analyze them, is that it can be difficult to interpret what's a planet and what's a disk. One very good way to distinguish a planet from a disk is actually the H-alpha emission. So you have to have some object that's quite massive in order to accrete gas from the surrounding disk material and generate that H-alpha signal. And with another observation, we were able to see H-alpha emission from PDS-70c also, and that was made by Sebastian Heffert, who's since actually migrated to the University of Arizona. This is something special, I think, for an adaptive optics system, is that we can actually put an eyepiece on it. So here you see Laird Close, who actually built the system and who's a professor here, looking at Alpha Centauri through the eyepiece on MEG-AO. And this is the image of what it looks like up on the top right. Not really something you can do science with, but something that's pretty fun. So here's another system. This one we imaged quite a bit more recently with the telescope a bit closer to home. So this is another system with one of these PDS telephone numbers. PDS stands for Pico dos Dios. This is a survey that was done just looking for unresolved infrared emission from young disks. So a lot of these young systems have these PDS names. So what you see here is a tricolor image of the disk on the left, and it's a bit difficult to interpret, kind of because we're looking at a kind of close to the signal to noise limit. But to help us interpret this, you see this model image in the center. So what we're looking at is an inclined disk of gas and dust, and we see the forward side of it brighter here in this image. And the back side of, I'm not sure if you can see the cursor. You can't see my cursor here, sorry. But you can kind of see the back side of the disk also peeking out on the left. It almost just looks like noise until you compare it to the model and see that that's actually kind of where the disk signal should be. There are some things that we don't really understand about this. I'm not sure if you can pick out what I'm looking at. But this kind of arc down here that comes off to the bottom left, I don't think we really have any explanation for that yet. Since the system is quite inclined, it's at about 40 degrees from face on, it can be kind of difficult to pick out different features. Like, is this another ring that gets lost behind this main ring, or possibly it's a spiral arm? And both of these would have different interpretations for the physics that are going on within the system and possible companions and that are orbiting within this gap or possibly outside of it generating these features. These observations were taken with the LBT, which is one of my favorite telescopes because it's kind of like a backyard telescope to those of us here in Arizona. It's only a few hours away on Mount Graham. You can actually drive up to the summit and visit this one if you want to. So these planets in PDS 70 are a few times the mass of Jupiter, and they're opening this wide gap. This system here, PDS 201, we don't know of any planets yet, but we expect that there are planets in this gap. And again, we could fit our own solar system multiplied by several times in size within this gap. So if there is a planetary system in here, which we believe there likely is, something has to clear this disk of material. It's likely much more massive than our own. But still not so massive that something else happens to the morphology of the disk. So we can ask the question of what if Jupiter were quite a bit more massive, kind of on the borderline between a planet and a star? What would our own solar system look like then? Or what might it have looked like earlier on in its formation? This image here of one of the more famous targets of the Hubble Space Telescope, and actually one that I think you can see pretty well with just a small portable amateur telescope also, the Whirlpool Galaxy, gives us an idea of what we might expect. So here we actually have two galaxies that are merging and colliding, and you see this spiral arm pattern in the more massive galaxy. You see one of the spiral arms even pointing at this companion galaxy that's perturbing the material in the main one. And recently we saw a very similar situation on several orders of magnitude smaller scale around a young star. So this is the HD 100-453 system. The main star here is about twice as massive as our own sun. It has a binary companion at about 100 AU or so. That's about 20% the mass of our sun. And this system is about 10 million years old. So again, less than 1% the age of our own solar system. And you see this disk of gas and dust around the primary, and you see this two-armed spiral pattern, much like what we saw in the galaxy on the previous slide. And also we see one of the arms of the protoplanetary disk, in this case, pointing right at the companion star. So this actually is a pretty good test case for models of how super Jupiters should interact with their birth disks. So the same models and same physics that result in the spiral arms in this disk, in this case, should work if this companion were quite a bit less massive, something like a 10 Jupiter mass planet, like the ones that I showed you in that movie of planets orbiting HR 8799 at the beginning of the presentation. And just to continue in the pictures of the telescopes from which these images were made, this one was made with the VLT in Chile. This is actually a system of 4 8.2 meter mirrors or 8.2 meter telescopes. They can all be used together, but this image was made just by using one of them, which is typically how the system is operating, with each one of them pointed at a different target at a time. So we can actually be sure that, or quite sure that this companion is the reason why we have these spiral arms in this system. So actually by observing this system for a number of years, so from the first observation in about 2003 until the most recent observation just a few years ago, we were able to see a few degrees of orbital motion of this companion. You see the measurements up in this plot on the top right. And then by generating orbits and fitting these to the data, we were able to learn about the orbit of this companion. And why we wanted to do that is that just by observing the system in this configuration with the companion projected to be about 100 AU away from the main star, that doesn't mean that that's actually their physical separation. Since we only have a TD image or 2D image, there are projection effects. And before we took these measurements on the top right, we thought that it could have been it was possible that it could have been the case that this companion were actually quite a bit further away, say 1,000 AU or so, and just projected to look like it's much closer to the system. But that's not the case. We actually see that it's on a relatively face-on orbit. So the separation that we see in the image is actually close to the physical separation of the system. And in this case, it's practically inevitable that you get spiral arms. It's actually very difficult not to get spiral arms when you have this sort of gravitational situation. And in the bottom, you see a model of this. So in this image, the companion is indicated by the white dot, and you see a two-arm spiral pattern that looks pretty close to what we actually see in the observation. So to conclude that initial question that I asked, how do planets form and interact with their birth disks? Some kind of basic conclusions that we can back out is that giant planets, kind of those on the order of the mass of Jupiter in our own solar system, should open these gaps. But more massive companions, those that are say about 5, maybe 10 times the mass of Jupiter, should generate these wide-scale spiral arms. So we can use this while we look at systems in which we only see the disks but not the planets in order to back out some information about what planetary systems we think are there. So now I want to show you a few images of these systems. And in these, we actually do know that the companion is there in most cases. So we can actually use these systems as test cases to say what the disk features should look like with the parameters of the known planets or stars that are in there. So I just talked about this one on the left here, HD 100-453. So this is a binary star system. It's about 10 million years old. But what if the system were a bit younger? So on the right here, you see a picture of AB Aurigae, taken again with the VLT in Chile. It's a few times younger than HD 100-453. And that means that this system hasn't had as much time for its material to be dissipated or cleared by the truncation of the companion. So you see this more extended spiral pattern. The companion's also a bit more difficult to detect, partly because there's a lot of gas and dust still in the system that's obscuring our view of it. But recently, we were able to take some observations that actually is showing us light from likely the planet. But if it's not the planet, then it must be coming from a disk around the planet, what we call or know as a circumplanetary disk. So you see this here, and this is a situation where actually this feature was seen in the images a while ago, but it was kind of one that's difficult to interpret and know that there's a planet there until you see a signal like H alpha emission that we saw for PDS 70. So this feature here, this kind of blob within this ring of the disk, also has H alpha emission. It also has a few other features that make us quite convinced that it's a planet. Sorry, I'm moving my cursor on this screen and I see that you can't see it on that screen. So I guess that's not a worthwhile exercise. You see these spiral arms also here, kind of in the center of the image, pointing at this feature that's indicated as a planet. That gives us some further indication. But what really helps is splitting this apart into different wavelengths. So here I'm showing the same image that you saw on the previous slide in blue, and now overlaid in red, you see data from a radio telescope. So this was taken with the Atacama Large Millimeter Array, also in Chile. And what's special about these wavelengths is that at about 1 millimeter or so in size, we get emission from larger particles in the disk. So this is showing us where the dust is located. And it's kind of trapped right outside of this location of the planet. This is also what the models tell us we should expect. This is known as dust trapping or dust filtration, in which the small dust is allowed to filter through the gap and the planet traps these larger dust particles at the edge. Here's another image of the system with the Hubble Space Telescope. You can see that there's a lot going on here, but when we zoom into the inner regions, you're able to see the light from the planet in two different epochs. So on the top, you're seeing the system imaged in 2007, and on the bottom, you're seeing the system imaged in 2001. And it's a bit difficult to see because the time scale is pretty long here. But if you draw a line on both of these images, you can see that this source is actually moved a bit. So in the top, it's kind of centered, and on the bottom, it's a bit to the right. So this is orbital motion that we're seeing of this source. And since it's at about 100 AU away, the orbital timescale is quite long. So we only see a little bit of motion despite having observed for 14 years. Here's some images of another system. So this is MWC 758. This one also has spiral arms and a candidate. This is what I was working on today. So I think this is pretty fun that I can just throw images that are pretty fresh into talks like this. What's special about this one is that it's also very young. So AB Aurigae, the one that I just showed you, is at the very top here on the left of this plot of temperature versus age. This is one of the youngest planets that we know about. PDS 70 also that I showed you is a bit to the right of this darker black line. And this black line here is showing you the possible values for this companion, which is a bit younger. So again, one of the youngest planets that we know about that enables us to study the physics of planet formation within its own system. And this one's also probably quite massive, something like, well, the minimum mass is something like 2 to 4 Jupiter masses. And we know that because of the spiral pattern. So where are we going with all of this? What we want to make is sort of an ensemble of these images of young planetary systems. And to look at their features in a kind of statistical context in order to learn about the different types of varieties of planetary systems that are out there, and to also link these to the more mature exoplanetary systems that we've been able to detect and study. But alongside of that, we want to be able to look for examples of what our own solar system looked like. We'll never be able to make an actual baby picture of our own solar system, but what we can do is make baby pictures of systems that are pretty similar to our own solar system. So this one here, I think, is probably one such example. You can picture having a system of giant planets like we have in our own solar system with Jupiter and Saturn fitting within these two main gaps. And interior to that, there's still plenty of material left over for forming the inner planets like our own Earth. Now, I want to tell you a bit about how these planets formed. And more specifically, we could rephrase this question as, what is the general formation mechanism for these wide orbit giant planets? Or asked another way, do they form like planets, or do they form more like failed stars? So in a bit more detail, there are two ways that we can imagine forming a giant planet. You can either have a bottom-up process, like this image on the left, where we're smashing these smaller building blocks of planets together into forming bigger ones. Or you can have a situation on the right, where a region of the disk becomes overdense and undergoes a gravitational instability that rapidly forms a massive planet, kind of all in one go. These are both physically plausible mechanisms, and they have some notable differences. Most notably, probably the time scale. So if you're building planets from the bottom up, this takes a lot of time. It takes a lot of time to smash small things together in order to build them up into bigger things. Partly is because at the very small particle sizes, when you smash them together, they tend to collide destructively and not constructively. So it can actually be relatively difficult to get these grains to stick together. And there are a number of other barriers also. Nature does find a way to overcome them. We do find rocky planets that were made by core accretion and giant planets that were able to accumulate gaseous envelopes afterward. But suffice to say that it takes a long time. And gravitational instability suffers the opposite problem. It has to occur very early on when there's still enough mass left in the system to trigger the instability. If the system's a bit older and more material is dissipated, then there just isn't any possibility for it to go unstable anymore. So these result in remarkably different populations. So this plot is showing the result of two different simulations, one making planets via the core accretion or CA method, and one making planets via gravitational instabilities or GI. And what this plot is showing is just the number of planets that you generate via these two methods as a function of mass. And you see that with core accretion, you end up with a lot of small planets and not a lot of bigger ones. And gravitational instability, you see the opposite population. You see much more of these more massive planets, things that we would typically think of as brown dwarfs above the 13 or so Jupiter mass deuterium burning limit. So this is what we should expect. And what do the observations tell us? So these blue data points here is actually the distribution of companions that we've measured from all of the planets that we've been able to directly image, brown dwarfs included here. And you see that overall the distribution does follow this kind of bottom heavy pattern. Most of these, in other words, were formed by a sort of bottom up core accretion type formation process. But there is a contribution above what we should expect from core accretion at the most massive side. So above about 20 Jupiter masses or so, there is kind of this excess of companions that we observe compared to those that we should expect from core accretion alone. But if we were to scale down the core accretion population synthesis predictions and add these together into a combined population, this actually fits the data quite well. So in other words, objects that are less than about 10 Jupiter masses or so, or most of the planets that we've been able to directly image, probably formed in a disk via some bottom-up process like core formation or core accretion. But above about 20 Jupiter masses or so, these are where these objects are more predominantly formed, kind of like failed stars. So I thought I would take more time to go through those slides. So I can take any questions on those now, or I do have some bonus slides for you, but maybe let's go for any questions on that first.
Okay, we're getting the microphone fixed here for me. So we're going to deviate some tonight from our usual format. So members just, expect a few changes. And we're going to go to right now a brief number of questions from Facebook. So do we have questions from Facebook? Terry is not finding them yet, but she's still looking. And there's none on Zoom. Okay, so we don't have questions from Facebook at this point. Okay, so what we're going to do at this point is we're going to thank our Facebook people for joining us tonight. We really are delighted that you come. We hope that you'll look at our website at tucsonastronomy.org. There's lots of different kinds of information and resources on there. And we meet the first Friday of every month at 6:30. So that we hope that you will join us again on next Friday and any Friday after that. And please, consider joining if you're really interested in the kinds of things that we do. So thank you for joining us tonight, Facebook.